So now we're going to continue our exploration of sound by considering what happens if either the source of the sound waves or the observer of the sound waves is moving. And this is a phenomenon called the Doppler effect. If you've ever, say, were in a car and you were driving past a jackhammer, you probably noticed that the pitch of the jackhammer seemed higher when you were approaching the jackhammer. And then when you passed the construction site and moved away from the jackhammer, you noticed that the pitch of the jackhammer now seemed to be lower. By the same token, if you've ever sat by, say, the side of a road or something like that, and you hear a car's engine approaching you, you notice that the engine notes seemed a little higher than when it went away from you, where it would then seem a little lower. Both of those are examples of the Doppler effect. So first we'll take a look at the jackhammer case. This is a case where the observer is the one doing the moving. So out over here somewhere is some source of sound waves. And what I'm drawing here are the wave fronts of the sound waves. They're propagating over this way. Now let's say you're here as an observer, but you're moving. So let's say you are moving with a speed v, and this is an O, not a 0. This is the velocity of the observer. For our purposes now, we'll say that v is the speed of sound. Oops. So let's say you're walking, if you're to just stand still, let's say all of these waves that I drew here would have passed your location in some time t. In some time delta t, we have this many wavefronts go through your location. But now if you're moving, let's say you are moving towards the source. In that case, in that same time delta t, you would end up over here. So this means in addition to all these wavefronts that you would have heard if you just plain stood still, the very fact that you're moving meant that you picked up a couple of extra wavefronts due to your motion. So if the waves sort of magically just stayed put somehow, when you walked from here to here, you would have walked through these two. But of course the waves aren't staying put, so in addition to these two, you also hear every wavefront that would have gone past your location anyway. So this means in this time delta t, you heard more wavefronts than was actually produced. Now obviously you can't keep this up forever. Eventually you're going to pass the source. So it's okay that you're hearing more wavefronts in some time than is being made. That's just due to your motion. Now, the derivation of the relation for what frequency you'll hear, I don't find terribly instructive, so I usually am just fine with quoting the result and taking a look to see if it at least looks reasonable. So this here is the frequency you hear. This F naught here is the frequency of the source. This is a naught, that's an O there. Then this is your speed, this is the speed of sound. So if you were approaching, you picked up some extra wavefront. So you heard more waves in some time delta t, say 1 second, than were actually produced. So the frequency you would hear would be higher, and you would pick the plus sign if the observer was approaching the source. On the other hand, if you were heading the other way, then that means effectively you're running away from the waves. And so these two extra waves, let's say, would actually not made it to your ear because you moved that far over. So then the frequency would be lower if the observer was receding from the source. Now, let's just make this concrete by thinking about what happens if you were moving toward a tuning fork that was playing concert A at 20 meters per second. So this would mean that our source frequency is 440 hertz. This is the agreed upon standard for what the note A should be until the conductor decides it should be something different anyway. And we said you were going towards at VO equals 20 meters per second. So just to estimate things, we already know that since you're approaching, it should sound higher. So you expect a number bigger than 440. Let's see what we actually get. So we can put in here, my F would be 440 hertz. 1, and here I'd be picking the plus sign because we're going towards. The speed of the observer is 20 meters per second, and let's use 343 meters per second as our speed of sound. That'll give us 466 hertz. So sure enough, you actually hear the frequency to be higher. Alright, so that's if the observer is moving. Now let's consider the case where the observer is stationary but the source is moving. And then eventually I will mention briefly how to put the two of them together if you need to. So if we have a source that's moving, I'm just going to represent the source with a dot. We can imagine it's a subwoofer or something like that. And I'm going to just mark what are hopefully reasonably uniform positions. So we'll say that this is where the source was at time 0, time 1, time 2, time 3, and then here at time 4. Alright, so, and we'll say that at each of these particular locations that this was a location where a wavefront was emitted. Let's also, just for the sake of argument, say that at location 4, the source is just now emitting a wave. So, assuming that you're moving slower than the speed of sound, and we'll deal with what if you're not in a bit. But assuming you're not moving at the speed of sound, or faster than the speed of sound, your wave from, oops, sorry about that. Let's try that again. There, something like that. Yeah, that's not too bad. Alright, so assuming that you're not moving at the faster than the speed of sound, which we'll get to in a bit, the wavefront emitted from location 3 will be in front of the source when it is at location 4. And by the same token, then we can follow back what about the wave that was emitted at location 2. Well, that's going to be the same kind of deal right there. That wavefront will have gotten in front of when was the one emitted at location 1, and so forth. So let's just draw one more. We'll draw the one for location 1 here. Actually, this one's probably a little too big. Oops. I did not mean to do that. There, that's a little better. All right, let's just do the one for location 1 and call it good. All right, that looks pretty good. So, and then I'm not, location 0 would be even further out. Oh, what the heck, let's just go for it. We're on a roll. There we go, something like that. These should be evenly spaced, but they're not. I mean, they are in reality, they aren't in my art. All right, so with that, we can go now and start to take a look. Whoops, my bad. There we go. Let's look at this distance right here. We can see here the wavelength. Let's say you are the observer standing over here. The wavelength here is shorter than the wavelength that you, corresponding wavelength that you would be seeing over here. So as the source moves toward you, that has the effect of causing the wavefronts to pile up. As the source moves away from you, if you were over here, that would cause the wavefronts to get stretched out. So over here, you would be hearing a shorter wavelength, higher frequency. And similarly, if you were over here, you would be hearing a longer wavelength, therefore a lower frequency. And again, I'll skip the derivation because it's a little tedious and not terribly instructive, and quote the result. The frequency that you hear will be the frequency emitted over 1 minus or plus the speed of the source over the speed of sound. There we go. And again, we will be picking the upper sign if you are approaching, and the lower sign if you are receding. So let's just go and do that same thought experiment. Let's say that you have a source that is approaching you at 20 meters per second playing concert A. So concert A, we said, was 440 hertz. This would be over 1, and since it's approaching you, it would be minus 20 meters per second over 343 meters per second, and you get 467 hertz. Hey, take a look at that. That is slightly different than what we have here, and that's okay. This is because with all of this stuff, there is one true observer, if you will. Because we reference the speed of sound, the one observer who can legitimately do all these calculations is the one who is stationary with respect to the air. So it shouldn't surprise us if the source or the moving observer get slightly different answers. Now you might concern yourself with what if they're both moving. If they're both moving, the deal is you have to think of this in 2 steps. You would first use the moving source relationship to get the frequency that someone who is stationary with respect to the air would hear. And then that would be the effective frequency that was emitted that the moving observer would concern themselves about. So if both are moving, the net result is that you combine the relationships. So you'll get that the frequency is the frequency at the source times 1 plus or minus V observer over V, divided by 1 minus or plus V source over V. And keep in mind all four signs are possible. It is, say, if I have a cop chasing someone on the highway, and the cop is going faster than the person on the highway, the moving source would be approaching the speeder on the highway, but the speeder on the highway would be receding from the source. So all four possible combinations of plus and minus signs can occur. So you have to think carefully about how each one of them is moving toward the other, not whether they're relatively approaching each other, whether they're relatively coming together or relatively pulling apart. When you go on and take a look at electricity and magnetism, this is going to be a difference. It will turn out that when you study relativity, special relativity, that all observers, regardless of how they're moving, all measure the same speed of light. And so it turns out that the corresponding Doppler shift equations for light waves will look different in order to account for that. And all that will matter in that case is whether they are just approaching each other or pulling away from each other. But with sound, there is a true fixed observer that is someone stationary with respect to the air. And so here all four possible signs are possible. Alrighty, so we'll finish this off by taking a look at what happens if you are going faster than the speed of sound. So if we have a source, that is moving faster than the speed of sound. So let's put my dots very far apart here, and I'm going to try to draw the same kind of circle things as before, and I hope it works out better. In fact, I'm going to kind of cheat it a little bit because I know what it should look like. Okay, something about like that. All right, now let's go pick out some circles. So that's not too bad. Oh. There we go. Let's do the next one. So here, since the source is moving faster than the speed of sound, let's try that again. There we go. Since the source is moving faster than the speed of sound, the source is outrunning its own sound waves. I just need to shrink these up a little bit. There we go. And then let's finally put one in here. Something like that. All right. That's probably as good as it's going to get. Yeah, we can make this look a little less awful, I suppose. There we maybe go. Well, I tried. So anyway, the deal is that all of these wavefronts pile up on what's called the shock wave of the system here. Go on. There we go. No, there we go. All right, fine. Shock wave. There we go. So all the wavefronts all pile up. And at points in between where you're not emitting a crest, it turns out that it will time out perfectly that what will be right here will be a crest. So all the crests pile up and they add up together. So there's an awful lot of energy that gets stored in these waves. So there are some, the classic fun example of this is if you crack a whip, that crack sound you actually hear is a sonic boom from these shock waves. The tip of the whip is actually moving faster than the speed of sound, and so what you are actually hearing is the sonic boom from the shock wave passing your ear. And of course, supersonic aircraft are a classic example. My grandmother used to live underneath a military training route for the Air Force. One time the aircraft were flying a little too low and a little too fast. She got visited about a week later by the Air Force, and they apologized very much for breaking her windows, and they fixed it. So, you know, there's an awful lot of noise that can be had from those. Or I should say they offered to fix it. So that's enough energy that, you know, from an aircraft flying several hundred feet above, it could break windows. If you've ever had an opportunity to hear a rocket stage come in for a landing, again, it's the same kind of deal. You'll hear these booms, and it sounds like the thing blew up. I actually happened to be present at Kennedy Space Center to watch the first ever successful landing of a Falcon 9 booster. And all of us in the observing area, because we weren't allowed to be any closer than 5 miles for safety reasons, all of us in the observing area, when we saw the rocket come down and the engine cut off, at that exact moment, because the rocket was moving faster than the speed of sound until almost the last second for landing, it was only at that exact moment that the shock wave actually made it to us. And we heard a couple of very loud noises, and everyone kind of thought for a moment, ooh, it blew up. And then we realized that we didn't see any giant flaming fireball or anything like that. And then we realized that that was the sonic boom from the rocket stage coming in, and that had indeed successfully landed. And just in case you think that was just me not thinking through my physics well enough, that also happened to be the case for the CEO of SpaceX. He happened to be outside, heard the big booms, and started promptly walking back into the blockhouse where everybody was, and getting ready to give another big pep talk when he saw everyone jumping up and down like crazy. It's like, oh, okay, I guess this is when we pull out the bottles of champagne that we had reserved for just such an occasion. Alrighty, in the next video we will start to concern ourselves with standing waves, so we'll catch you on the next one.